Good day everyone, my name is Sriram Gopalakrishnan and I will be presenting the work on FastMap-D, which is a way of embedding directed graphs in potential fields. This is a joint work with Liron Cohen, Sven Koenig and Satish Kumar. Before we delve into the details, I'd like to give a quick overview to frame the research work in the right setting and give the motivation. Embedding graphs in Euclidean spaces is useful for many problems in AI. Perhaps the most obvious is for path planning and the multi-agent meeting problem, but it actually applies to many more problems. For example, community detection and social network graphs, representing the knowledge base for question answering systems, and more generally, it can be helpful for any problem where the information is represented as a graph. But Euclidean distances are symmetric and directed graphs can have asymmetric distances. So how do we handle the asymmetry? The idea is to learn a potential field function and overlay this on the embedding space as illustrated to account for the asymmetry. To help your intuition, think of the potential field due to gravity. The cost of going uphill is different from the cost of going downhill. So what we do is embed the average distance between two nodes, A to B and B to A, and then account for the difference with the true distance in each direction using the potential field function. To help understand FastMap, we will quickly go over the evolution of the algorithm from its beginnings to its present modification that supports directed graphs. The original FastMap algorithm came from the data mining community. In it, each entity was an abstract object, not a node in a graph, and they assumed that pairwise distances are computable in constant time. For example, if the objects were DNA strings, we can compute the distance between any pair of objects in constant time. The algorithm embeds these distances in a Euclidean space of a specified k dimensions and would run in linear time. So how are these embedding coordinates computed? Let's start with the coordinates for the first dimension. We first heuristically select 2 points A and B that are far apart. We call them pivot points. Note that they are heuristically chosen and they are not necessarily the furthest points. That would take longer order of n square comparisons, and the original FastMap data mining algorithm ran in linear time. The coordinate for A would be 0 in this first dimension, and the coordinate for B would be the distance from A to B. These are our pivot points. Then for every other node I, we use the distances to the pivot points to compute a coordinate value xi as a perpendicular projection onto the line between A and B as illustrated. Not all of the distances between nodes is accounted for in this first dimension. This leads us to the recursive step in the algorithm. To understand the recursive step, let's take 2 points I and j that are not the pivot points. Part of the distance between them is captured in the first dimension, which use the pivot nodes A and B. The remainder is projected onto the hyperplane perpendicular to the first dimension, and this residual distance is computed by the formula shown. Note that the distance between A and B is fully accounted for in the first dimension, and A and B project to the same point in the hyperplane, which is what we want. The embedding process previously discussed is repeated with these residual distances. This recursive step is repeated for as many dimensions as desired. This succinctly is the original FastMap for abstract objects. FastMap was then adapted for undirected graphs in the following way. The challenge in graphs is that pairwise distances are not computable in constant time. It's a function of graph size, but all is not lost. Since we need the distance between A and I and B, where A and B are the pivot nodes and I is any other node, we can get this from the shortest path trees rooted at nodes A and B. So the cost of computing pairwise distances, AI and IB, is amortized by computing and saving the shortest path trees rooted at A and B. The rest of the algorithm follows the same procedure as before. And in this way, FastMap handled undirected graphs. The final and current step in the evolution of FastMap is to directed graphs, and this brings us to the subject of our work. With directed graphs, we have the problem of asymmetric distances between pairs of nodes, i.e. the distance from I to j is not equal to the distance from j to I. So what we do is embed the average distance between nodes in the first k-1 dimensions, and then the last or kth coordinate is actually a function over the previous k-1 coordinates. This is a potential function, and what we learn is a potential field over the embedding space. This function is learnt such that it accounts for the difference between the directed distance and the average distance embedded. Please note that one limitation in our current approach is that the graph must be strongly connected. That is, there is a path between all pairs of nodes. This is not the same as fully connected, but strongly connected. Let's see an example to help understand our approach. Let's say the distance between nodes I and j was 2 and the distance between j and I was 8. The average distance between them is 5, and this is what we try to embed in the Euclidean space using the first k-1 coordinates. The difference in the last coordinate, or the kth coordinate, between I and j is what would account for the delta between the average distance and the directed distance. So if we were going from j to I, the difference in the kth coordinate would be 3. And with the average distance of 5 gives us a total distance of 8. In the opposite direction, from I to j, the difference in the kth coordinate would be -3, which when added to the average distance gives us 2. And that is how we can account for the asymmetric distances. We embed the average distance and account for the difference with a potential field function. The natural next question is, how do we learn this potential field function? In our work, we represented it as a multivariate polynomial with unknown coefficients, where the variables of this polynomial are defined by the previous k-1 coordinates. We used distances obtained during the embedding process of the prior k-1 dimensions to define constraints on the unknown coefficients. We then solve for these coefficients using linear regression. One can use OLS, lasso, which is L1 regularized regression, or other regularization variants. We got the best results with lasso. Please note that the ML module used for learning psi, the potential field function, is a plug-and-play component. It can be learnt with neural networks or any ML module that does regression. In order to test our method, we used benchmark maps from moving.ai and converted the undirected graphs to directed graphs. We did this by assigning a virtual height to each node based on its xy coordinates in the map. This height was used to assign asymmetric edge weights between connected nodes. Combined with the existing graph structure from the maps, we were able to generate strongly connected graphs with asymmetric path distances between nodes. While making our presentation, we fixed an implementation mistake and got better results than those that appear in the paper. We will present the better results here. Our code will be available on GitHub for you to play with under the name of the paper FastMap-D. Now let's look at some results. In all experiments, we tested our algorithm on 2 directed graph versions of each benchmark. The one on the left uses a height function defined by a polynomial function of the map coordinates, and the one on the right uses an exponential function on the coordinates to define the height. Let me reiterate that the heights are then used to assign asymmetric edge weights in opposing directions between every 2 connected nodes. So an exponential function gives us more asymmetry to the edge weights. Also, in these results, we measure the error via normalized root mean square error. It is the standard deviation of the errors normalized by the average distances of the paths in the graph. This metric helps us compare the results across different graphs. One important point to note: in all these results, the potential field function is a second-order polynomial function over the first k-1 coordinates. So that would be all first and second-order terms. These terms would be d1, d1 d2, d1 square, where d1 and d2 are coordinates in different dimensions. Now in this map, for the polynomial height function on the left, you can see that FastMap-D performs significantly better than the FastMap algorithm, which only embeds the average distance. The last coordinate, when used for the potential field, is much more powerful in representing directed graph distances than using it to represent more of the average distance between nodes. For the exponential height function on the right, we see a similar trend, but the normalized root mean square error is not quite as low for the same settings. The more asymmetrical and complex a graph's distances are, the harder it would be to capture these distances. This graph comes from a slice of Boston's city map. We see similar trends here, but notice that in the exponential height case, embedding only the average distance results in an error greater than 1.0. This means that the standard deviation of the error is larger than the average path distance in the graph. However, with FastMap-D, we are able to bring it down to 0.3. For this maze map, the difference between using just the average distance and FastMap-D is not as pronounced, but still appreciable. Finally, in what was the hardest map to capture the distances, this randomized map from the benchmark with an exponential height function required 30 dimensions for FastMap-D to bring the NRMSE down to 0.35. In these results, we vary both the number of dimensions and the degree of the potential field function. In the plot on the left, the x-axis is the number of dimensions. The plot on the right is the same data with the degree of the polynomial on the x-axis. As one might expect, the higher the degree of the potential field function, the lower the NRMSE. Now let's take a look at some results with using fully connected neural networks. When we use the raw xy coordinates of the map to represent the input nodes, it's very hard for the neural network to learn the distances between nodes, as illustrated in the second column of this table. The error seldom drops below 1, and if so, only by an insignificant amount. However, if we use the embeddings from FastMap and use the neural network to learn the potential field function, the performance is spectacularly better and much better than using lasso with 15 dimensions and a second-order polynomial function. The trade-off is that neural network training takes more time and more training data. For both the neural network settings, we gave all the shortest path tree data for the 15 embedding dimensions from FastMap-D with lasso. So we think that if training time is not a concern and is an upfront cost that can be incurred to learn a better potential field function, then using a neural network could work better. A point that we want to highlight is that these results show the benefit of using a more informative representation as input for an ML module. In this case, it's embedding versus raw coordinate representation. In this paper, we presented a generic framework for representing directed graphs in embedding space, independent of a specific application. In the future, we will look at the performance in specific applications, such as path planning and multi-agent meeting problem, specifically in comparison with differential heuristics as advised by one of our reviewers. As mentioned, this framework is more general and extends to other problems involving graphs, so we would like to investigate its efficacy in search and analysis on, say, social network graphs for detecting communities, clustering, and so forth. Lastly, we would like to relax the requirement of needing strongly connected graphs for our method. In summary, graph embeddings can be used for a variety of AI problems, and FastMap can efficiently embed undirected graphs. FastMap-D is an effective generalization for directed graphs by embedding distances within a potential field. What we hoped to get across in this paper is that our embedding method works for different graph configurations and that the asymmetric distances can be captured well. The output of FastMap-D is a representation that can then be used by ML modules for downstream tasks like path computations and clustering. Thank you for listening to our idea.